Hello students, today we are going to discuss about atmospheric stability. In this presentation, we will be discussing about the following, that is the introduction to atmospheric stability, lapse rate, environmental lapse rate or ELR, adiabatic lapse rate or ALR, and the atmospheric stability based on the relationship between ALR and ELR. Let us imagine a air parcel or a plume being emitted from a tall stack or chimney of an industry, or a air parcel being emitted from a vehicle. The air pollutant emitted are transported and dispersed in the atmosphere. The effective dispersion of the pollutant depends upon the degree of stability of the atmosphere. Now, the degree of stability of the atmosphere means whether the atmosphere is unstable or stable. An atmosphere is said to be unstable if the air pollutant that is being emitted undergoes upward vertical movement and is completely dispersed into the atmosphere. This happens mainly when there is solar heating and wind in the atmosphere. For example, during hot summer afternoon, there will be sufficient solar heating and wind present, which will allow the pollutant to be completely transported and dispersed into the atmosphere, thereby diluting the concentration of the pollutant in the atmosphere. An atmosphere is said to be stable if the pollutant that is being emitted is not properly transported and dispersed into the atmosphere. This happens when the atmosphere does not have proper solar heating or wind. For example, during early morning, when the atmosphere is very calm and gloomy and when there is no wind, the pollutants are not properly transported and dispersed into the atmosphere. Next is lapse rate. Now, what do you mean by lapse rate? The decrease in temperature with respect to altitude is called lapse rate. The lapse rate is represented as minus dt by dz, where T is the temperature and Z is the altitude. This decrease in temperature with respect to altitude is seen in the troposphere up to a height of about 10 kilometers. There are mainly two types of lapse rate, environmental lapse rate and adiabatic lapse rate. Environmental lapse rate or ELR. The environmental lapse rate or ELR is the rate of decrease of temperature with altitude in the stationary atmosphere at a given time and location. It is not affected by the saturation of water vapor in the atmosphere. It is the actual lapse rate at any point due to the actual prevailing conditions. It is represented as dt by dz ENV is equal to minus 6.5 degrees Celsius per 1000 meters. That is, there is reduction in 6.5 degree Celsius for every 1000 meters we go upwards. Now, before going into what is adiabatic lapse rate or ALR, let's see what is a adiabatic process. If a system has no exchange of heat with the surrounding, that is, there is no energy transfer into the system or to outside the system is said to be undergoing adiabatic process. The adiabatic process can be better explained using this figure. Just imagine a parcel of air as shown in figure 1. The parcel of air can be something like a puff of smoke being generated from a tall stack or from a vehicle. Now, as we know, when a puff of air is generated from a tall stack or from a vehicle, it will try to move vertically upwards. So, the figure 2, 3 and 4 in sequence explains how the parcel of air is slowly moving upwards and how it is expanding. So, as it expands, it slowly moves into an area of reducing pressure, and the distance between the particles is increasing, as a result of which the temperature within the parcel is getting reduced. We should know that since this is an adiabatic process, this puff of air or the parcel of air is not exchanging any temperature with the surrounding. The reduction in temperature is only due to the expansion of the air puff and the reduction of the pressure inside the air puff. Now let's see what is adiabatic lapse rate or ALR. Adiabatic lapse rate is actually the theoretical lapse rate. That is, it does not take into consideration the temperature or the pressure or density of the surrounding air. ALR is the rate at which the temperature decreases with altitude when the air is either dry or moist. Air is moist when it is saturated by water vapor and dry when there isn't much water vapor. The ALR for dry air is denoted by DALR and for wet or saturated air is denoted by WALR or SALR. The dry adiabatic lapse rate or the DALR is represented by the letter gamma, and gamma is equal to dt by dz adi, that is equal to minus 10 degree Celsius per 1000 meters. That is, with the increase of altitude of 1000 meters, there is reduction in temperature of 10 degree Celsius. The WALR or SALR is usually 1/3 of the dry or DALR. WALR or SALR is independent of the altitude. The atmospheric stability conditions can be explained by comparing the ELR and the ALR. That is, the comparison between ELR and ALR gives an idea about the stability of the atmosphere, that is, whether it is stable or it is not stable. We should remember that ELR is the actual lapse rate at a particular position at a particular time, and it may be influenced by the surrounding temperature, pressure, density, etc. Whereas ALR is a theoretical lapse rate and it is not influenced by the surrounding temperature, pressure, density, etc. Basically, there are three types of atmospheric stability conditions or lapse rates. First one is when ELR is greater than ALR, the atmospheric condition is said to be unstable. When ELR is equal to ALR, it is neutrally stable condition, and when ELR is less than ALR, the atmosphere is having a stable condition. Let's see what happens when ELR is greater than ALR. When ELR is greater than ALR, a rising air parcel cooling at the adiabatic rate will be warmer and less dense than the surrounding, as you can see from the figure. The air parcel at the bottom is the one which is warmer and is less dense than the surrounding atmosphere. As it moves upwards, it enters into a region of reducing pressure and thereby it reduces its temperature. So it becomes buoyant and continues its upward motion. This lapse rate is called superadiabatic. The atmosphere is said to be unstable. There is thorough vertical mixing of the pollutants with the surrounding, and the pollutants are dispersed quickly and completely. When ELR is equal to ALR, the rising air parcel will have the same pressure, temperature and density as the surrounding environment, and there will not be any buoyant force. The parcel of air neither tends to return to its original position nor it tends to continue its displacement upwards. This type of atmosphere is said to be neutrally stable. When ELR is less than ALR, a rising air parcel becomes cooler and more dense than its surrounding. The air parcel tends to fall back to its original position. As you can see from the figure, the air parcel is cooler than the surrounding and the air parcel sinks back to the original position. The lapse rate is called as subadiabatic. The atmosphere is said to be stable. Under this condition, there is very little or less vertical mixing of the pollutants with the surrounding, and the pollutants can disperse very slowly. The three conditions, that is the superadiabatic condition, or the unstable condition, the neutrally stable condition, and the stable or the subadiabatic condition, is shown with this figure. You can see in the first case the air parcel is rising and it is a unstable condition or superadiabatic condition. In the second case, the air parcel is sinking and it is a stable condition or it is a subadiabatic condition. In the third case, the pollutant is neutral condition, that is it neither moves upwards or neither sinks downwards. It remains at the same position where it has been emitted. So that's all about the atmospheric stability conditions. Thank you.